Hey, let's talk about networking costs in AWS, specifically in the context of Kafka and other distributed systems that replicate data. Before we start, we have to go over the concepts which AWS gives us. So AWS has regions and availability zones. The way to conceptually think about it is that AWS has this big network of computers across the whole globe, and different areas that have computers are called regions. Those regions can be in countries. Countries can have multiple regions. It's literally just like one part of a country. Let's say I find like a 100-kilometer field outside and I say, this is my region, Stan 1. And that's really what it is. So here you see it's basically across the whole world. And I'm going to use London as an example, the UK region in AWS. Each region has multiple so-called availability zones, or AZs, or zones. Conceptually, you can think of it as a building, as a data center building. An AZ can have multiple buildings, so that's a detail, but I'm going to use building in this example because it's easier to conceptualize. So in this case, we have 3 buildings in London. One is near the city of London, one is in the south of London, and one is in Hyde Park. Now, in reality, this would be outside of the city, but go with the example. Also, excuse my AI-generated image of London, but it's accurate enough. It's not exactly accurate, but it works. And yeah, these regions, these AZs, are called 2A, 2B, 2C. They have their own names. And AWS charges you differently depending on how traffic goes between regions, between availability zones, or how it goes outside of the AWS network, the whole wide AWS network. There are 3 types of charges: internet charges, cross-region charges, and intra-region charges, or within the region, stuff that goes within the region of AWS. Now, internet is the most expensive one. It goes from 5 cents to 9 cents a gigabyte, and it depends on the region as well. Some regions, if you're egressing data out of a region, out to the World Wide Web, which, by the way, World Wide Web here can mean anything outside of AWS. It could be going to GCP, to Azure, to some local provider, to your local computer, whatever. That's the terminology. That's the most expensive part of AWS. And some regions have higher egress costs than others. So again, it really depends on which region you're in. Then you have cross-region costs, which is data going between AWS regions. So this time you're not leaving the AWS network, you're still inside it, and you're just moving, let's say, from Spain to New York or something like that. And the third one is intra-region, or like cross-AZ, where it's in AWS, it's in the same region of AWS, and goes between machines. So here it could be between these 2 data centers in London, let's say. I have some examples. The internet traffic, first of all, is when data goes outside of the AWS network. Here, distance doesn't matter at all. You could move data out of a building in London that's owned by AWS and move it to a building owned by, let's say, Google, and you're still going to pay the internet costs. Or you can move it from London to South Africa or wherever, again, to a building owned by somebody else, and you're going to pay the internet costs for egressing. Those are 5 to 9 cents a gigabyte, so it's the most expensive one. It scales really fast when you're pushing a lot of data. Then you have the cross-region charges, which is within the AWS network, from London to New York, let's say, it costs 2 cents to move a gigabyte. Again, this depends on the regional pairing. Some regions are more expensive. I think South Africa had very expensive costs. India, some parts have much more expensive cross-region charges. And then we have the cross-AZ, which is within the same region. So again, we have the EOS2 region, the London region of AWS. And if I'm moving data from one data center to another, I'm going to pay 2 cents a gigabyte for that data moving. So it's a little bit interesting how I can move my data from London to California for 2 cents a gigabyte, traveling all across that space. And it costs the same as moving it between 2 buildings that are less than 100 kilometers apart in London. So that's a funny thing to note. The other thing is same AZ traffic, which is data basically going from one building to the same building, basically between 2 machines in the building. Now, again, there could be multiple buildings, so it could be one building to another building that are right next to each other, but the price is basically free for these things because it's in the same AZ. This is usually the best connectivity you have. Now, there's a little bit of a subtlety here where this same AZ traffic applies only if you're using the private IP of your EC2 box, and that's where the trickiness comes. In AWS, we have these things called VPCs. VPC stands for Virtual Private Cloud. It's basically a made-up virtual network between machines. VPCs have to be inside the same region, so you cannot have a VPC from London to New York. No, it has to be inside London only. And VPCs can have EC2 instances, VMs, that are across different AZs. So you can be in any AZ here, and it's going to be part of the same VPC if you configure it. EC2 can only be in one VPC at a time, obviously. So in this example, I have 6 machines. 3 are in VPC A, and the other 3 are in VPC B. EC2 machines have 2 IP addresses each that they publish. One is the public IP that you can reach from, if it's exposed, even from Google Cloud or any other cloud. And then you have the private IP that you can only reach from within AWS. And even then, cross VPC, you can't access the private IP. So the private IP of a machine is only accessible by other machines in that same VPC by default, unless you do some shenanigans to open that, that connectivity up. But here by default, these 3 machines can connect to each other to the private IP easily, and these other 3 machines in VPC B can also do the same. But cross, they cannot do that. So one machine from VPC B cannot connect to the private IP of VPC A. And this is where the cost comes. When you're using the private IP in the same availability zone or the same building, let's say, you're paying for nothing. It's the same AZ, so you get the free intra-AZ costs, which is 0 cents a gigabyte. But if you're using the public IP, if you're connecting to the public IP, which you would usually do when you're connecting cross VPC, you're going to pay 2 cents a gigabyte. So again, we're reaching this scenario where you're moving data within the same building. The data is not leaving the building. I think AWS has proxies that don't let the data go out and back. It's optimized like that. But you're paying 2 cents a gigabyte. And then you get into this ridiculous situation where it costs the same for me to move a gigabyte of data from London to New York as much as it does to move it from my one machine in London to its neighbor machine right next to it, again, in the same building, right under the same lights. So it's a funny situation. This is why you want to use private IPs, and we'll get into that in a little bit, but I told you I'm going to talk about distributed systems and Kafka. So what about Kafka? How does Kafka work here in this scenario? Well, Kafka is a distributed system. It replicates data between brokers, and to get high availability and to get high durability, you want those broker failures to be non-correlated. That's why you put brokers in different buildings or different AZs, so that if one building catches fire, the other AZs get to live and your system still works. In this topology, I have a very simple one. It's 3 brokers in the same VPC, in the same region, just living in 3 different AZs. They're using the private IP for connectivity because usually you would deploy your distributed system in the same VPC. Yet you still pay costs because remember, the data is moving to AZs and you're always paying that cost regardless if it's the private or the public IP. So this is sort of what a Kafka cluster can look like. Where it gets interesting is when you introduce clients to the mix. With clients, let's say your producer client, your consumer client, those things usually live in they live in the same AZs, but they usually live in different VPCs. But to get the AZ picture right here. Now, Kafka remember that in Kafka, you only write to the partition leader. So out of 3 brokers that are replicating a partition, only one is leading, and that one broker that's leading that partition is going to live in a particular availability zone, right? And then you have many partitions, and then you have many clients connected to many partitions, so you get this extreme amounts of cross-current communication. But to simplify everything, I've used 3 partitions here. I have a typo, but it's partition 1, partition 2, partition 3. And all of your producers and consumers, they live in every AZ again, but again, for simplicity, I'm just using one AZ here, which is AZB. In AZB, we have many consumers and producers, and they produce and consume from basically every partition, let's say, or from many partitions that live across availability zones. So you can see that here the consumers and producers get to consume and produce for free from the partition leader that's in the same availability zone as them, which is B. But they also communicate to 2 other brokers that are in other AZs, and then they pay the 2 cents a gigabyte cost, right? Now, again, the math gets tricky here, but simplifying everything, all else equal, if everything is balanced, if your partition leaders are balanced across the brokers, if your brokers are balanced across the AZs, and your consumers and producers are also evenly balanced across the AZs, you're always going to get 2/3 of client traffic crossing AZs, and 1/3 is going to be in the same AZ. If you don't believe me, run the math, but that's how it is. And now we have to introduce VPCs into the mix, because usually your client applications are going to live in different places. Your client applications are, let's say you have a payments team. They have their own apps, their own microservices. They have their own VPC. You have your fraud detection team or fraud team. They have their own VPC as well. So you have many VPCs here. Again, I've simplified it here to have just two VPCs, the Kafka VPC and let's say the client VPC. In this case, these VPCs, remember, they cannot talk to each other's private IP. So the consumers and the producers can only talk to the public IP of the Kafka broker here. And you don't get this effect where 2/3 of your traffic you pay for the cross AZ charges. No, you pay for 100% of your traffic, because even when it's in the same AZ now, this link that used to be free here, even though it's in the same AZ, you pay 2 cents a gigabyte because remember, you're using the public IP to connect, unless you do something to expose the private IP. So recapping this is cross AZ clients in Kafka. If you're using the private IP, you're always going to have 2/3 of the producers moving data and paying that 2 cents a gigabyte charge. And consumers are also going to be 2/3 unless you enable KIP 881 or KIP 392, which enables you to read data from the same AZ. That's an optimization you can run. It's not hard. And replication, I'm not touching replication here, but replication, you're always going to pay 2x your produce, because whenever you write 1 gigabyte to one broker, that broker has to replicate to 2 other brokers for fault tolerance, and those 2 other brokers are going to be in 2 different AZs, so you're paying 2 times your produce for cross AZ charges. One thing that's, again, not accounted for here is when you're buying Kafka from somebody else. So if you're buying Kafka from Confluent or from some managed service that offers Kafka, usually by default, they give you a public IP that's authenticated. So the IP is publicly exposed, and you get like a password to authenticate to that. And again, even if your clients are in the same AZ as the broker, because you're using the public IP, by definition, you're going to be paying some amount of money just for that, 100% of the traffic, as we talked about. The way EC2 or cross AZ charges work in AWS is, again, you pay 2 cents a gigabyte, as I said, but these cents get split. So if I'm moving 1 gigabyte from Stan 1 to machine Stan 2, Stan 1 pays 1 cent a gigabyte for egressing the data out, or for moving the data out of it, and Stan 2 pays 1 cent a gigabyte for receiving the data in. In a SaaS provider scenario, these costs get split. So I'm going to use Confluent again as an example. If my producer is pushing 1 gigabyte to Confluent, I'm going to pay 1 cent for my producer for the fact that I moved that data out of my AZ or out of my public IP, and Confluent is going to pay 1 cent a gigabyte for receiving that. Similarly, if I'm consuming, Confluent is going to pay 1 cent a gigabyte for moving that data out of their broker, and I'm going to pay 1 cent a gigabyte for receiving that data in my consumer. Now, on the left side, the SaaS provider costs are usually accounted into the price of the SaaS service, but the right side of the costs are usually not accounted for. And the tricky thing here with customers is they get different bills for this. You know, the SaaS provider bill is easy. Confluent gives you the big bill and it says, okay, you used this much Kafka, that's what you have to pay. But on the right side, that bill gets bundled into all of your other AWS costs. And when AWS gives you the monthly bill that's huge and says, okay, networking costs 2 million or whatever, you have no idea what part of this was for my consumers and producers and my Kafka costs, and what part was the rest of my huge AWS infrastructure that I have. So it's tricky to figure these things out. And that's why I think many people most likely miss this type of cost analysis, and I've seen reports in the wild that do miss it as well. So again, if you're using cross AZ clients or same AZ, if you're using the public IP, you're always going to pay 100% of the cost, regardless. There's no network optimization. You're going to pay to the nose for the networking, especially with consumers, because remember, Kafka is a system that's made to have high fan out. If I'm writing 1 gigabyte of data to Kafka, I'm expecting to read it 3 or 5 times. And that's why the consumer fan out, like it gets really expensive if you can't optimize the consumers. And that's why KIPs like this are so important, to make consumers read from the same zone. I don't have it visualized here, but you can make consumers read only from brokers in the same zone. That's why these KIPs are so important. But if you can't enable the private IP connectivity, those KIPs are useless because you're still going to pay costs. And I don't have much time left, but when I say clients, I mean everything. I don't only mean consumers, producers. I mean Apache Flink, I mean Kafka Connect, I mean Kafka Streams, I mean KSQL, I mean your normal Spring Boot consumers, producers, etc. So yeah, it gets really expensive, and you really have to think about these things. And that's all. Like, there are some solutions to this. Usually some clouds will give you ways to do this. I'm going to end this at the 15-minute mark, so I'm not going to talk to all of them, but some of the solutions are also paid. So if you're using Transit Gateway or Private Link, you're still paying for it. So again, you have to think very carefully what you're going to do and how you're going to optimize your Kafka network costs in AWS.